All right, so there are two techniques for doing this. I'm going to just kind of, I think everybody's going to be okay by just learning the first technique, and the second technique is going to be kind of a waste of our time because they're ultimately the same thing. It's just the order in which you do these steps might be a little bit different. We said yesterday we'll start with this equation, and solving that equation for 3 theta is not a difficult task, right? So first thing we'll do is add 1 to both sides. So it's going to be 2 sine of 3 theta equals 1. And then you would divide both sides by 2, right? So we're going to try to isolate sine of 3 theta. And when we do that, sine of 3 theta ends up being 1/2. Okay? Is that something we do? Okay. Now the next step is that we don't always care that it's 3 theta. What we're trying to do is always trying to solve for the argument. Okay. So the question we ask is, when is sine equal to 1/2? Sine of an angle is equal to 1/2 at what angle? 30 degrees or pi over 6, right? And however you want to do it, it's fine. Doesn't matter with me. If we go, well, let's just do it with both. Okay, so let's go pi over 6 or 30 degrees. That's what our angle should equal, right? Our angle here is no longer theta, it's 3 theta. So we just solved for 3 theta. Does that make sense? Okay. Now, that is only one solution that exists on the unit circle when sine is 1/2, right? What's the other angle when sine is 1/2? 5 pi over 6 or 150 degrees. Okay. And I just want to, just so that we can visually see these as being different. Let's do 3 theta. Let's do the degree ones in blue, and we'll do the rating ones in red. Ultimately, when you're doing them on your own, you only need to do one. Okay, just do radians, just do degrees, whatever you're most comfortable with. I'm actually more comfortable with radians. I'll kind of explain why here in a little bit. On a test, you just got to make sure that you understand what if they say on the interval from 0 to 2 pi, then you got to do it in radians, right? If it's 0 to 360, then you do it in degrees. If it says nothing, do what you want to do. Okay. All right. So looking at this, the next step that we do is that and this is, obviously if I've got 3 theta equals pi over 6, then I can solve for theta, right? And that's going to generate one solution. Okay. But then creating the next solutions that mimic that will be maybe not as obvious if I don't do this step first. What I want to do first is add 2 pi k to these. I basically want to create those infinite solutions. Okay, so I'll add 2 pi k to that one, and I'll add 2 pi k to that one. If I didn't do that, basically I'd have to know what the period is. We got to take 3 theta, or 2 pi divided by that b value. Does that make sense? And know that the period is going to be 2 pi over 3. Here, doing it this way, adding that 2 pi over k, doesn't make me have to think about the period for this horizontally compressed sine function. It just generates it on its own. Okay, if I add that 2 pi k first, before I divide both sides by 3. So if I divide both sides by 3, now I don't like dividing by 3 when I got fractions involved, right? Rather multiply by a third. So I'm going to have theta, multiply this by a third, I get pi over 18, right? Multiply this by a third, I get 2 pi over 3 times k. And that should make sense to us that we're always, to find infinite solutions, we're always adding our period times k, right? Well, when your argument is 3 theta, you have a horizontal compression, which reduces now our period to 2 pi over 3. But that is generated automatically if I do that step first. add the 2 pi k to the pi over 6. Down here, I would do the same thing. Okay, divide both sides by 3 or multiply by a third. And I'm going to get 5 pi over 18 plus then 2 pi over 3 times k. Is that okay with everyone? Okay, now just drawing kind of a comparison and then doing it in degrees. Instead of adding 2 pi k, you'd add what? 360k. Okay, now it might make more sense instead of, like, you can still multiply by a third. Okay, or now here, because these are not fractions, it probably makes more sense for people to divide by 3, right? Divide by 3, you get 10 degrees plus, what, 120k? And then here, you're going to get theta to be divided by 3 again, so you get 50 degrees, plus then 120k. Does that make sense? All right. And this should make sense, guys, that, you know, if I were to take pi over 18 and convert that, multiply by 180 over pi, it turns into 10. If I take 5 pi over 18, multiply by 180 over pi, it turns into 50. Yeah, that should all make sense. Okay. Now here's the thing. We have to figure out what other solutions. We've now condensed so our sine function normally looks like that, right? Between 0 and 2 pi. Okay. And if that's 1/2, we have 2 solutions. Well, what that 3 theta does between now 0 and 2 pi, okay, is it makes that thing oscillate 1 time, 2 times, 3 times. 3 times. And now if I put in that 1/2, how many solutions do I really have? 1, 2, 3, 4, 5, 6, right? This is only showing me one solution of pi over 18 and a second solution of 5 pi over 18, right? Now the plus 2 pi over 3k is the index tool to get me into the next solutions. But we have to know how to use that, okay? And basically what we do, all right, we're going to let k trying to see the best way we can write this. Let k obviously be an element of your integers. Okay. On, let's just say, the interval 0 to n minus 1, where n is the coefficient of your argument. That kind of makes sense? So what that does is k is an integer, okay, and it's on this interval, so k is going to start on 0. It's going to go to 1, it's going to go to 2, it's going to go to 3, it's going to go to 4, all the way up to n minus 1. Well, in this case, n is our coefficient on our argument. So it's going to go up to 2. Does that make sense? So you're going to go k equals 0. So I'm always going to go k equals 0, k equals 1, and then k equals 2. And I stop with k being 2 because that's n minus 1. And now I'm just going to evaluate these angles on those values of k. So this first one, if k, and just doing the radians, if k is 0, I just get pi over 18, right? Pi over 18 is one solution. If k is 1, okay, now here's something I like to do. If this is pi over 18, I'd prefer to write this as 12 pi over 18. Does that make sense? Okay, that's still 2/3 pi, right? Okay. But now if k is 1, basically all I'm doing is adding 12 pi to the numerator, right? That's the reason why I prefer working with radians. Because you're going to see here in a moment when we work with degrees, it's adding numbers much larger than just 12. Okay. Now I've got a common difference. This is actually an arithmetic sequence. Okay, the common difference being 12 pi over 18. Okay, so I'm not going to substitute 2 in here and evaluate. I'm just going to add 12 pi to this previous numerator. And I get 25 pi over 18. Is that all right? The same thing down here then. 5 pi over 18 is the first number, or first angle when k is 0. Okay, now think about this. I'm still adding the same 12 pi over 18, right? That number there and that number there, they were the same. They're the same period. So as I was working through here, and it was 12 pi over 18, 12 pi, I was essentially adding just to the numerators. It's going to be the same thing here. So I'm just going to take 5 pi plus 12 pi and get 17 pi. And I'll take 17 pi and add 12 pi to it, and I get 29 pi. So the general approach, guys, if you were to look in a textbook or something like that, they're going to tell you, take k equals 0, k equals 1, k equals 2, and substitute and evaluate each time. So evaluate 6 different times. And every single time you do that, you're going to find out that you're just using a pattern. So why not use the pattern to start with? Okay? Figure out what these infinite solutions are so that you can figure out what when k equals 1 essentially is. And then when you look at those two, there's a common difference. And take that common difference and just add it on to every other solution that you have. And that will get you your 6 solutions that you need. Now, if I was doing it in degrees, obviously, it'd be 10 degrees first. Okay? And then when I add 120, so that becomes 130. And then when I add 120 again, so it becomes 250. The reason I like to work in radians instead of that is because I don't like adding 120. I like to add 12. Okay, it's a smaller number, right? You'll see another example here in a little bit where we're adding like I think 90 to like 115 or 105 or something like that, and it just gets mental math wise a little bit. It's not something we can't do at this stage, but it's something maybe we don't want to do. Here we would get 50 degrees, and then here it'd be 170. And then here would be 290. And those would be the 6 solutions, either in radians or degrees, for that equation. Checking yourself, guys, you can obviously use any calculator that you want. Okay. Give me a second. All right, so
who leaves to work at like 9:30?
I sent that at like 8. Oh. Yeah, I just checked it. Okay, let's look at this solution. Let's look at these. What do we have? 2 sine of 3x minus 1, right? Okay. And if we're looking on the interval between 0 and 2 pi, okay, we end up seeing those intersections. Now we're looking at intersecting the x-axis here. So our solutions were, what was 1? Pi over 18. So there's that one, right? And here's the thing, guys. When we created this pi over 18 plus 2/3 pi k, that's actually a formula that will give me if I just write it this way, okay, it's going to ask me here to create a slider, but k has to be a what? An integer, okay? So if k, obviously, it just slides through there if k is anything. Well, let's just let k be an integer now, so we'll make this increment by 1. And as we work through, okay, so there's pi over 18. There's the next one. You see how they mimic each other? They're the same point, but this one is in the second cycle, right? So that was it 13 pi over 18? Yeah. And then this one would be 25 pi over 18. Okay? And then once I go to the next one, you see how we jump out of the interval? However, if they don't give me the interval, if they don't care what I'm solving this on, and they want the infinite solutions, we could be done right here, right? We only had to do this because we wanted the solutions that were inside 0 to 2 pi. Okay. The other point was 5 pi over 18, right? So 5 pi over 18 plus 2/3 pi times k. All right. Now, if I look at those, so now we see those two things kind of moving together as k increases, right? And now if k goes beyond 2, that means we've now found essentially our 7th and 8th solutions, which we don't need those, or want those in this case. That's something we can do. Okay. Now, we can obviously change this stuff. We can make this, let's do this with cosine. Let's put, let's put √3 here. I don't know, not all that easy to do with Word. All right, so let's go 2 cosine, and let's change this to, let's go 4 theta. Minus √3 equals 0. Okay. So first thing you're going to do is what? Add √3 and then what? Divide by 2. So it's not difficult. That's going to end up, if you kind of do that, both those steps maybe in your head, you get cosine of 4 theta equals √3 over 2, right? All right, so cosine of 4 theta equals √3 over 2. So then 4 theta, our angle, and again, this is where we don't really care that it's 4 theta right now, our angle is going to equal radical 3 over 2 at what x value? Or sorry, the x value is radical 3 over 2 at what angle? Okay, 30 degrees. Or 150. And if I was doing it in radians, it would be, oh, sorry, yeah, you're right, sorry. That's 330. 330, my fault. I was thinking sine. So 330. And this would be what, pi over 6 and 11 pi over 6. Okay. Add to this 360k. 360k. Add to this 2 pi k. 2 pi k. If I was doing this with tangent, what would I be adding to it? Just pi k. Okay. So now, go through and solve for theta, right? So theta is going to be, now this is what kind of stinks with the degrees, is 30 divided by 4, right? It's not a really nice number, correct? Okay. What's it give you? So 7.5 degrees plus then, okay, so 360 divided by 4 would be 90, right? So 90k. This one here then, what's 330 divided by 4? $82.5. Yep. All right, so but down here in the radian one, it's much easier, I think. Okay, now I multiply by a fourth, I'm going to get pi over 24, right? Multiply by a fourth, I get plus, now it's pi over 2k. I'm going to write that as 12 pi over 24k. Because I want that to be in I want a common denominator. And that's just multiplying by a fourth there. So now down here, it's the same thing. It's 11 pi now over 24 plus then 12 pi over 24 times k. Now, here's my argument of why I'd rather do it in radians, and why I'm not going to go any further with the red one. I'll leave that up to you if you want to. But 7.5 plus 90, that's not too bad, right? But what's 7.5 plus 90 plus 90? That's not too bad. But then plus 90 might start getting a little bit uglier, right? 82.5 plus 90. And then add 90 to that, and then add 90 to that. That mental math I don't like, okay? But down here, okay, with this stuff here, if k is equal to 0, this first one right here is going to be just pi over 24, right? Okay. If k is equal to 1, it's 13 pi over 24. If k is equal to 2, it's going to be 25 pi over 24. Okay, isn't it much easier just to keep adding 12 to that numerator? And then when k is 3, we're going to add 12 to that, so it'd be 37 pi over 24. And those are the four solutions for theta. I should have wrote theta here is equal to that. Theta is equal to that. Those are the four solutions for theta in that first equation. Now, if I do the same thing in that bottom one, we're going to start with 11. So in this bottom one here, 11 pi over 24 for the first k equals 0. When k equals 1, we'll then add 12 pi over 24 to that, so it'd be 23 pi over 24. K equals 2, it'd be, 35 pi over 24. And then when k is 3, it's going to be, 47 pi over 24. Okay? And that, I think that's just a lot quicker way of doing the problem. That's why that kind of mental math, guys, I think is one of the reasons. There's several reasons, but one of the reasons why we do deal with radians. It's more natural. Okay, simple mental math, that kind of thing. If we understand our fractions, the thing to think about there is obviously we're interested in making sure our solutions are between 0 and 2 pi here. If my denominator is 24, then 2 pi would be 48 pi over 24, right? Do we see how all of these solutions are less than 48 pi over 24? That's something to think about, because that's going to be something that we have to mess with in the next type of equation, because it's going to be still a multiple angle equation, but it's going to be of that version. Okay, and let's actually, we did tangent in the last class. Let's do this first one here. Won't let me get back into how I edited that. Let's do this one as sine instead. So I had radical 3 sine of theta over 2 minus, let's do it this way, because that's not going to be really nice. Let's go do this. A lot of times what they're going to do is just create an equation initially to get you in a habit of doing this process, an equation that when solved is going to give you like sine of whatever is equal to radical 3 over 2 or radical 2 over 2 or 1/2 or the negative versions of those, because then you can quickly generate values off the unit circle. But it doesn't have to be. I mean, we could get sine of theta over 2 is equal to 0.17 if we wanted to, okay? And then have to use our inverse keys on our calculator and all that garbage. But all right, so solving this, then we're going to get sine of theta over 2 is equal to root 3 over 2, right? Root 3 over 2. So here's the issue. We're going to solve for theta over 2 now, solve for our argument, and sine is that radical 3 over 2 at what angle? 60 degrees, right? Let's just do everything in radians right now, so it'd be pi over 3, correct? And the other time that sine is that would be at 2 pi over 3, right? Those are the two situations in which sine is equal to root 3 over 2. Now, the problem is, when we go through this using k idea, because our argument is not a integer multiple, we can't do that rule where we say we start at k being 0 and we march through up until n minus 1. Because here n is 1/2, right? And if I go n minus 1, I get negative 1/2, and that's not an integer, obviously, right? So if k is going to be an integer, then the way we use that, the interval in which we use it should be in terms of integers, okay? But it's not if we have this 1/2. So we don't know initially how to use k, okay? But what we do know is that k is an integer, and it's going to start at 0. We're going to always start at 0. And then all we do is we continue to evaluate, adding when k is 0, we figure out what that is, then go k equals 1, figure out what that is, go k equals 2, figure out what that is. And every time that we figure out what our angle is at particular values of k, we just need to go back and check, is that inside or outside the interval that the question was asking about? Okay? If it's inside, it stays a solution. If it's outside, it's not a solution, and then that means we can actually stop, because any other values of k greater than that one that provided the first one outside the interval is also not going to be inside the interval. It's also going to be on the outside. So, kind of do that and explain that, but we'll kind of walk through that process here as we evaluate this. So what they'll say, guys, is they'll say, okay, well, we're interested in maybe 0 and 4 pi. Let's just start there. 0 to 4 pi. Might be 0 to 2 pi, might be 0 to 6 pi, might be 0 to 8 pi, might just be 0 pi. It could be anything. Okay? Let's say we're interested in looking at solutions on that interval. So what we do is the same exact process. You're going to add to this 2 pi k. You're going to add to this 2 pi k, because that's the period of the sine function, right? Okay? Now, just like the last one, you're going to solve for theta by multiplying both sides by what in this case? 2, right? So you can now get 2 pi over 3, 2 pi over 3 plus 4 pi k. This one here gives me 4 pi over 3 plus 4 pi k. I like to write that as 2 pi over 3 plus 12 pi over 3. Okay, is that still 4 pi k? And the same thing down here, 4 pi over 3 plus 12 pi over 3k. And I also like to take my interval and rewrite that in terms of thirds. Is this still 4 pi right there, 12 pi over 3? All right, so this is what we do then. Like I said, in the last one, because this argument was an integer coefficient, okay, we could predetermine that k had to be 0, 1, 2, and so forth, right? And we could stop. Here we can't do that. Here we have to say k is 0 and evaluate. Well, if k is 0, you get here 2 pi over 3, right? If k is 0 down here, you get 4 pi over 3. Are both of those between 0 and 4 pi? Yes. Okay. The reason I like to change this to 12 pi over 3 is because now all I have to do, because these are in thirds as well, now all I have to do is compare the numerators, right? If these numerators are less than 12, I keep it. If it's over 12, I get rid of it. Okay. So now I let k be 1. Well, if k is 1, I'm going to now have 2 pi over 3 plus 12 pi over 3, and it gives me 14 pi over 3, right? Is that between 0 and 4 pi? No. So that tells me that is not a solution that I'm interested in because of the interval that they defined. If it was 0 to 6 pi, then I keep it. Does that make sense? Okay. But here I kick it out. It's not a solution. So hopefully it makes sense then that when k is 2, that's not going to be a solution either, right? It's going to be a bigger number than 14 pi over 3. So once I find my first non-solution or first solution outside the interval that's being asked for, then all other values of k that are bigger are going to be outside that solution as well, or outside the interval as well. Okay. Then, okay, so hopefully that makes sense down here. That 4 pi over 3 is going to only be the one solution because I'm going to still be adding 12 pi over 3 to this, right? And this number is bigger than that one. So this k equals 1, and when I want to eventually be 16 pi over 3 is obviously bigger than 14 pi over 3. So 16 pi over 3 doesn't work either. Does that make sense? Okay. So those are my two solutions on that interval. If we go and graph this, kind of graph wait, 2 sine, this was square root of 3. Let's say, so I'm just going to make this x real quick. Okay. So that is the 2 sine of 1x minus root 3, right? Let's compare that to x over 2. So inside there, you're seeing you've got, if I look at the interval between 0 and 4 pi now, inside there you get 1, 2, 3, 4 solutions, right? But now when I make this the half angle, put this x over 2, see how it stretched it out? And when it stretches it out, it pulls those original solutions outside of that interval. So now I only have 2 solutions in there. Okay? And those 2 solutions should be of the form. We have 2 pi over 3 plus what was it, 4 pi k? Yeah. 4 pi times k. And then we had 4 pi over 3 plus 4 pi times k. Gives me those 2 solutions, right? Okay. Now, as k grows, when k ended up being 1, you see how I gave those first 2 solutions outside? And that would have been the, 14 pi over 3 and 16 pi over 3. If I'm not really interested in a particular interval, you see how this allows me to march through and find all those solutions, right? Okay? So that's something to think about as well. If they do not tell you the overall interval that you are interested in, okay, so this thing here is gone, then this is your solution, and that gives you the infinite solutions, right? My hope is, my overall task for you guys, so on your test maybe will be, or even the final, come up with the infinite solution. Come up with the expression that provides the infinite solutions. Because once you have that, then it's just a matter of substituting k and seeing if that result, then when you substitute, produces something between 2 numbers that you're interested in, 2 interval values. Does that make sense? Okay. So if you can come up with what's in yellow there, that's the main task. That gives you all your solutions. Then it comes down to an issue of whether, okay, of all those solutions, which ones are they really asking about? And then substitute and figuring that out. Okay. Is it okay with everyone? Okay. If it was tangent, I know I started the question with the tangent, but the tangent, you're going to do the same thing. You just got to realize then with the tangent function, instead of adding 2 pi k, you're only adding pi k, right? Same thing with cotangent. Those are little things to kind of pay attention to and remind yourself as you're preparing for that test on Friday. remind yourself those little key features and details about tangent, cotangent that are a little bit different than sine, cosine, secant, cosecant. Work on that take-home test, or not take-home, the practice test. Come tomorrow with questions over it. My goal tomorrow, guys, is if we want to go through all 8 of those questions or all 10 of those questions, we can do that, okay? If you want to go through 4 of those questions and then similar examples of those 4 questions, we can do that, okay? But I want to use all that 50 minutes tomorrow just reviewing for that test, okay? As of right now, it looks like I will not be here Friday, so there will be a sub here. I got a professional day out at Rhodes that I have to go to.